In three-dimensional lattice gauge theory, a novel approach is presented to enhance the signal-to-noise ratio of observables, focusing on the SU-2 model. By leveraging complex contour deformations of the path integral, significant signal-to-noise ratio enhancements have been achieved in two-dimensional gauge theories with open boundary conditions. To adapt this method to higher dimensional theories and generic boundary conditions, two key innovations are introduced: gauge fixing and a neural network definition of the deformation. The gauge fixing innovation allows for the effective application of complex contour deformations to three-dimensional spacetime dimensions. The neural network definition of the deformation enables a more precise control over the deformation, leading to substantial improvements in the signal-to-noise ratio for Wilson loop measurements. The study demonstrates that the proposed method can achieve signal-to-noise ratio enhancements of up to 3 orders of magnitude. This significant advancement has important implications for understanding the behavior of gauge theories in higher dimensions and under various boundary conditions, contributing to ongoing research in lattice field theory. The presented method has the potential to overcome limitations in current lattice gauge theory simulations, enabling more accurate investigations of gauge theories in higher dimensions. The research was presented at the 40th International Symposium on Lattice Field Theory, where experts in the field gathered to discuss recent developments and advancements in lattice field theory. The paper presents a novel approach to mitigating the signal-to-noise problem in lattice gauge theory calculations, focusing on the area law scaling of Wilson loop expectation values. This method employs complex contour deformations of the path integral, acting directly on linked degrees of freedom, applicable to theories with generic boundary conditions. The authors demonstrate this approach in an SU-2 pure gauge theory in 3D, achieving exponential improvement in the signal-to-noise ratio of Wilson loops over a wide range of areas. They also explore lattice volume dependence and discuss generalization to SU-n and higher dimensions. The work is built upon the Euclidean path integral definition of the expectation value of a quantum operator, a fundamental concept in lattice gauge theories. By optimizing deformation choice, the authors show noise reduction in Euclidean time correlation functions of Wilson loops in 2D-U-1 and SU-n lattice gauge theories. This research contributes to solving sign problems, such as those arising from a non-zero chemical potential or real-time path integral, and has potential applications in machine learning, artificial intelligence, and computer science for statistical noise reduction and signal enhancement. Neural network contour deformations offer a promising approach for lattice gauge theory, where the crucial task is to integrate over gauge field configurations. To achieve this, a discretized action is employed, and operators acting on these configurations are represented. A key insight is that complexification and analytic continuation are essential for the path integral, enabling its continuous deformation into the complexified domain without altering its value. This deformation facilitates the estimation of novel observables, which possess identical expectation values but potentially distinct variance properties. Furthermore, the Wilson gauge action is introduced, and its complexification is explored in the context of signal-to-noise problems in Wilson loops. By leveraging these techniques, researchers can potentially overcome limitations inherent to traditional methods, ultimately enhancing the precision of lattice gauge theory calculations. The section of the research paper discusses neural network contour deformations for lattice gauge theory. It begins by defining the inverse coupling constant and the oriented plaquette at position x. For the SU-2 gauge group, the parameters u mu, x, and p mn, x, are elements of SU-2. The action is analytically continued using inverses p-1 mn, x, and u-1 mu, x, in equation 5. The paper then adopts the Bronson parametrization of SU-2 matrices, defining the path integral in equation 7. This path integral involves the normalized SU-2 par measure and the set of gauge links parametrized by the angular variables. The section also discusses constant deformations, which have been used successfully to reduce Wilson loops variances. These deformations involve constant shifts into the imaginary direction for the variables thm, x, phi1, mu, x, and phi2, mu, x, fixing the endpoints at 0 and pi, 2 for thm, x. The deformation map is defined in equation 8, including a shift for the periodic variables phi1, mu, x, and phi2, mu, x. The Jacobian of this transformation is trivial, and the normalized Haar measure is not change. The new observable q, theta, is defined in equation 10, used to compute the expectation value of the original observable. The authors explore a neural network-based approach to contour deformations for lattice gauge theory, focusing on the maximal tree gauge fixing scheme. They first restrict the path integral by fixing to a maximal tree gauge and then deform the remaining degrees of freedom. The choice of how the fixed links are arranged significantly affects the signal-to-noise ratio improvements. The authors have found that the most significant reduction in variance is observed by choosing the maximal tree gauge defined by equations 11, which specify the arrangement of fixed links. To obtain the most significant reduction in variance, the authors also choose the arrangement of the Wilson loop observable to lie in the 0, 1 plane with the lower left corner located at the origin. For small lattices, optimizing the deformation parameters directly on gauge-fixed configurations provides orders of magnitude improvement of Wilson loop signal-to-noise ratios. However, for larger lattices, the abundance of parameters quickly leads to an overfitting regime during optimization. To overcome this training issue, the authors reparameterize the shift field, delta I, mu, x, as the output of a neural network, phi, mu, x, w, where w is the set of weights defining the neural network. This new parameterization reduces the overfitting issue. The authors use the U-net architecture to produce phi, mu, x, w, which takes a constant input given by a collection of Boolean fields specifying the gauge-fixed links and the links making up the Wilson loop. The U-net is constructed to reduce the lattice dimensions by a factor of 2 along each axis while increasing the number of channel dimensions by a factor of 2 in each coarsening step, and doubles the lattice dimensions along each axis while reducing the channel dimension in each prolongation step. In this section, the authors introduce a novel approach to computing constant shift deformations for lattice gauge theory using neural networks. They employ a U-net architecture that takes gauge fixing and Wilson loop masks as inputs and outputs the components of delta I, mu, x, which represent the shift field. This method significantly improves upon previous methods by reducing variances on lattice sizes 163 and accelerating training on smaller lattices. The U-net consists of a combination of convolutions, down convolutions, up convolutions, and copy and add operations. The input channels correspond to gauge-fixing masks and Wilson loop masks for 3 orientations of links, while the output channels correspond to the components of delta I, mu, x. The authors also introduce a decoder network that uses convolutions to transform a shift field from a smaller volume to a larger volume for lattices with identical beta and gauge fixing schemes. This architecture is depicted in Figure 2, where the mean of the operations and boxes are the same as in Figure 1. The use of the U-net in training not only allows for reaching much smaller variances on lattice sizes 163 but also enables much faster training on smaller lattices by reducing the total number of updating steps to the weights. For these reasons, all results in this work are based on this U-net parametrization of the shift field. The author's approach coarsens the lattice dimensions by a factor of 2 until they reach 23 at the coarsest level before prolongation. To enforce the gauge-fixed links, the authors multiply by a mask as a final step, ensuring that phi, mu, x, w, equals 0 for all mu, x where u mu, x, are gauge-fixed. Researchers have developed a novel method to improve the signal-to-noise ratio of Wilson loops in 3-dimensional SU, gauge theory with periodic boundary conditions. This approach utilizes neural network contour deformations, trained to minimize the variance of the Wilson loop, which is crucial for reducing computational costs associated with training on larger lattice volumes. The technique involves training a U-net to produce a shift field delta I, mu, x, for a Wilson loop size of r times tau on a smaller lattice volume. A decoder network is then used to transform this shift field into one suitable for a Wilson loop size of 2r times 2 tau. Comparing the deformations produced from a U-net targeting the final lattice geometry versus using the U-net output at smaller volume together with a decoder network, both reach the same variance improvement once properly trained. The transfer learning scheme is essential for training on lattice volumes 323, where direct training costs become large. Results are presented for lattice theories with fixed beta equals 3.75, periodic boundary conditions, and 3 choices of lattice sizes: 83, 163, and 323. For each ensemble, 1.5 times 10 to the 5, 1.1 times 10 to the 5, and 2.4 times 10 to the 4 configurations are generated for training, and 500 configurations for testing, respectively. No significant autocorrelations of plaquette values are observed within these configurations. The optimal constant deformation is obtained by directly training UNETs for the 83 ensemble, while for the 163 ensemble, the decoder architecture is used. For the 323 ensemble, the decoder network previously trained for the 163 ensemble is fine-tuned with fewer than 10 to the power of 3 steps of weight updates, a much lesser amount of additional training than direct training. To avoid numerical stability issues, training is done by minimizing the logarithm of the variance of the targeted Wilson loop for each geometry using the log sum exp function. The 1 component of the untraced Wilson loop is measured and optimized. Training is performed on a single compute node with 8 NVIDIA A100 GPUs, using mini-batch sizes of 32 configurations per GPU with the default settings of the Atom optimizer. The resulting improvement factors in the Wilson loop variance are shown, with up to 3 orders of magnitude of variance reduction obtained at the largest Wilson loop studied. As the area is increased, increasing improvements are found. The reduction in variance obtained using these techniques is nearly independent of the total lattice volume, depending much more strongly on the Wilson loop geometry. Neural network contour deformations for lattice gauge theory yield variances of improved Wilson loop observables, showcasing efficacy across 83, 163, and 323 ensembles. Figure 3 illustrates the ratios of variances between original and improved Wilson loop observables, attributing the achievement to the maximal tree gauge fixing scheme, U-net parametrization of the deformation, and decoder networks with transfer learning. This approach can be easily generalized to 4D lattice gauge theory by employing 4-dimensional convolutions and a 4-dimensional maximal tree gauge. Furthermore, the method is applicable to other choices of NC, including the SU-3 gauge group, by working with corresponding Bronson angular parametrizations. Future exploration avenues include optimizing gauge fixing schemes, which significantly influence final variances of improved observables. The current maximal tree gauge fixing scheme obscures the translation symmetry of the lattice, making volume averaging expensive. Alternative gauge fixing schemes, such as partial subsets of a maximal tree gauge, may simplify the process and yield similar or better variance improvements. Exploring contour deformations beyond simple field-independent deformations, such as the Fourier series expansion presented in 5, may further boost performance and eliminate the need for gauge fixing altogether. These refinements hold potential for enhancing the accuracy and efficiency of lattice gauge theory computations. The paper by Yin Lin explores the application of neural network contour deformations in lattice gauge theory, a crucial area of research in theoretical physics. It builds upon previous studies on this topic, including works by Fradkin and Susskind, Detmold et al., Aurora Science Collaboration, and Witten. The paper also draws from the field of image processing, specifically the U-net architecture proposed by Ronberger et al. The challenge lies in accurately computing the expectation values of observables, which is achieved through the use of Markov chain Monte Carlo algorithms but can be computationally expensive and suffer from autocorrelation issues. To address these challenges, the author introduces a new method that utilizes neural networks to approximate the deformed contours in the complex plane, allowing for more efficient computation of expectation values. This method leverages the idea of deforming the integration contours in the complex plane to avoid singularities, as suggested by Bronson. By employing a neural network to approximate these deformed contours, The author demonstrates how this technique can significantly reduce the computational cost associated with traditional methods. The neural network used in this study is trained using a loss function that measures the difference between the approximate and true expectation values, facilitated by the use of importance sampling to reduce the variance of the loss function. The resulting neural network model is then applied to a variety of test cases, including the computation of expectation values for the Polyakov loop and the plaquette operator in the two-dimensional Ising model. The results demonstrate the efficacy of the proposed method, showing that the neural network can accurately approximate the deformed contours and compute expectation values with high precision. The computational cost of this approach is significantly lower than that of traditional methods, making it a promising tool for future research in lattice gauge theory. The paper concludes by discussing potential avenues for future work, including the application of this technique to higher dimensional systems and the development of more sophisticated neural network architectures. It also highlights the potential for this method to be applied to other areas of theoretical physics, such as quantum field theory and statistical mechanics.